All right, so after working on many examples directly finding general derivative of any given function, then it's now time to put that into all that details into some further understanding. And so let's once again look back at that beginning function where I begin our lecture with. So that function was f of x equals the simple function x squared. And so in that function, its graph is here, that famous graph for the x squared function. F of x equals x squared is here. That's nice parabolic shape. Okay, and that's just to remind everyone that. And so now we found that its derivative, the derivative in respect to this function was f prime of x equals 2x. So we found that this is the derivative, and we also agree that the derivative of this function is also a different function. It's also a function, another function. They're not necessarily the same function as the beginning one, but these are two different functions. So now it's time to investigate, it's time to understand and put the graphs together and understand how these two functions relate with each other graphically, or do we have some kind of relationship? Of course, besides the derivative, the relationship we already knew, but is there some other relationship that we can recognize? We're going to investigate graphically and numerically. Okay? And so allow me to get back on the graphing screen right here. Get back on the graph right here. But so in our very first function, f of x equals x squared here, this is the first function, the beginning function, f of x equals x squared. And so I use a point where I can drag along the graph to start doing that interactive sort of animation thing right here. But this is any point on the graph. Okay, that's why I can drag it along. Okay, so these are points on the graph. And let's say now I'm going to put a tangent. So anywhere I put a point, any x value that on the graph that I can put a point, then I am going to put a tangent and observe how the tangent line is changing as I'm moving my points. And that's the whole point of being able to find a general derivative for the function, because we can quickly and easily find the equation of a tangent line, and that actually is the algorithm behind the scene that any computer software would do that, to quickly get the tangent line equation and plot that together with our main function. And so now, let's say we got a point here on the graph. Our graph is in red, and this point here is, let's say, somewhere the label is saying minus 2.47, and the output value is 6.101, something like that. It's a point on the graph. And now on that graph, I put up that tangent line. And so the tangent, this line in green is tangent to our graph in red, okay, at that particular point. And now I'm going to start dragging, and as I drag, we're going to start noticing a few things. So the tangent value, the slope of the tangent value changed. Okay, so at this point I'm dragging my points through a lot of different places already, and my tangent line does change. The slope of my tangent line changes as well, changes accordingly. But here's the thing: no matter how I change, no matter where I drag my point to, if you can notice, as long as I still stay, so the x-axis is here, so as long as I still keep my point here to the left-hand side of the y value, or in other words, if I keep my x value anywhere still less than 0, keep my x value negative, being less than 0, see, to the left-hand side of x equals 0, x equals 0 is right here, then you can notice that commonly our slope of the tangent line is a negative slope. And the tangent itself, no matter how it, the tangent is acting as, it's kind of rotating and changing slope, but in the end, as long as this point is still to the left-hand side of x equals 0, then our tangent line here maintains a negative slope because it's pointing down. And so now your eyes, when you're looking at this, when you're looking at this, can see that, can tell that for yourself. And then there's this special point x equals 0 when I actually hit that right there. Then, and of course, I'm not skilled enough to get the exact spots, But when we hit to 0 right here, precisely 0, so let me zoom it in a little more. Okay, but when we hit to exactly 0, right, x equals 0, then we maintain the horizontal tangent line where we have a slope 0. And then immediately as I start swinging my point to the right hand side, meaning now anywhere on my right hand side of this parabola, my x value of the tangent point is positive, greater than 0, or to the right hand side of x equals 0. And look at how the tangent line behaves. The tangent line now is going to start switching to rising and having a positive slope. The line itself, see, no matter now where I put, but as long as I stay to the right hand side of x equals 0, then my tangent line has a positive slope. All my tangent line here, any tangent line to the right hand side of this graph is a line that's rising up, pointing up. And so now that kind of brings a nature, because so we already understand that when the tangent line is pointing down, or any line is pointing down from the left to the right, that means the slope here is negative. So let me swing back to our writing board right here. Okay. So the behavior that we want to notice here is right through the graph is that when x is less than 0, let's consider that into our graph I shown earlier was split into 2 separate zones. So when x was less than 0 as one zone, then it looks like the line where the tangent line was always doing this. From the left to the right, the tangent line was pointing down like that, right? Slanted and pointing down. So this is another way of saying we have negative slope there, right? Any tangent line when x was less than 0 was having negative slopes. And I use plural here as indicating we can have infinitely many tangent lines, but when we're still less than 0. So negative slopes here, any of those tangent lines had negative slopes, then that means generally we can conclude one thing. And remember again, slope of the tangent line, slope generally mt is less than 0. That's what negative slope is. But slope of the tangent line is equal to the function's derivative at whatever x value that is. And so in that way, we can make a further conclusion that in the way how we saw, in the way how we observed through the graph, then for this function in particular, then the derivative of the function for anywhere x less than 0 is going to be, we're going to know for sure that our function has a derivative negative. It has a negative derivative. And so in that way, the same way how we saw that earlier through the graph, when we switch to when we switch to an x value greater than 0, then our tangent line from the left to the right points up like that. So any tangent line like this, we refer to them as having those tangent lines or having positive slopes. Okay, and so positive slopes, that means mt is greater than 0, and that's also an mt slope of the tangent line is the same as the derivative of the function, again the general derivative of the function. And now so in that way ultimately we can conclude that so for this particular function, when x is greater than 0, then our derivative of the function is positive derivative because the tangent line was pointing up like that. So once again, let me demonstrate through the graph like that once again. All right, so to the left hand side, or when x equals 0, when x is less than 0, then we have the tangent line is pointing down, negative slope. The line itself is falling down, dropping down from the left to the right. But when we switch to somewhere x is greater than 0 to the right hand side, the right side of this parabola, then our tangent line is pointing up, having positive slope. Okay, and that's how I was making that conclusion earlier over here. Okay, and further, when we get into specifically it was such a challenging time for me when trying to get that exact point right here, but when x equals precisely 0 on the x-axis, then we came to having a horizontal tangent. Our tangent was like this, horizontal tangent. And so having a horizontal tangent like that, then that means the slope of the tangent line was equal to 0. We already knew that through algebra. And that means our derivative of the function of the original function also equals 0. I mean, I'm showing that property in regards specifically about this function f of x equals x squared. So now, putting that together, then generally we can draw an overall understanding that when, now let me put the graph back again, okay? But any time that our function, so any function, let me put the graph away. But so any function now, as long as, doesn't matter here we have a function being x squared over here, but on any function, as long as we can recognize a zone or a domain or a small interval where the tangent line points down, like in this case right here, and in that case, generally we have the derivative gonna have to be negative. And then in our graph of the function, if we have any interval where if we would place a tangent line, okay, and the tangent line looks like it's pointing up, any tangent line in that zone looks like it's gonna point up, then we're gonna know for sure that our f prime there in that zone has to be positive. And so now let me write down that generalization right here for any of us. And so what I see here, okay, so we given with any function f of x, then, okay, so if the slope of the tangent line is positive, right, then that also means our f prime, the function f prime we know, the point now is that f prime we know as a function, even though we don't know the graph of that yet, but it has to be a positive function. And then if we know for our function, our original function, that if we place a tangent line and graphically we recognize that our slope of the tangent line is negative, the tangent line is pointing down, then that means the same thing as our derivative as a function. For sure is going to have negative value in that interval. And then specifically, if our tangent line is horizontal or slope equals 0 for tangent line, then it's the same as our, at that particular value, we're going to have f prime, the function, I mean the derivative as a function is going to carry an output value equals 0. And so let me quickly demonstrate that into in a different graph right here. Okay, so the next graph that I'm about to show, well, we actually don't need any of that. Let me just quickly fix that right here. All right, so now let's look at something like this. And we don't have to know what shape this graph is. I mean, what function comes up with this graph. That's not the point, okay? The point here is, so now in this graph, I put these two special points here, x equals -2 and x equals 2 on this graph for everyone viewing this video to recognize a certain things, right? But, so now, if I place a point, and this point currently where I place it, the x value is less than -2. So right now we're going to look at the interval from anywhere from -infinity to -2. And I mean excluding -2. Then if we, what's your prediction? It looks like if we place a tangent line anywhere to the left hand side of -2, or x is less than -2, then what's your prediction? I predict that my tangent line is going to have to be a positive slope. Okay, and so drawing from what we've learned previously, then in this particular function, since for this particular function right here, then let me get back to my screen right there. Okay, and so for the current function that we've seen on the graph right there, and also let me put the graphs together. All right, so now having the graph there with the function you are seeing on screen, then with that kind of function, so let f of x be, and this is not even a formal example yet, it's just something that I demonstrate the idea right here. And so let f of x be given as the graph, right? Or as in the graph. Then for now, in the way how the graph look, and I put those two special points, then I know for sure that f prime, even though, see, the point is we didn't know what function that was to give us such a strange looking graph right there. And so in that way, we don't know, honestly, we don't know how to find f prime. But we know for sure one thing, f prime of x must be positive, okay, for x being less than -2. Pause the video. Take a moment to observe the graph closely and understand that for yourself right here. All right. So hopefully you had a moment to think about it. And once again, the reason I can make that conclusion, because see, no matter where I put my tangent point, but as long as I put my tangent point somewhere to the left-hand side of x equals -2, so to the left-hand side of -2 means x is less than -2. And that's what this is, okay? And that's how observe my tangent line in green right here. This is positive slope. And so the general conclusion about this, even though we only observed the graph and we did not know the actual function here, so that we did not really know what that derivative of the function, but we can directly observe the graph based on the relationship between the graph here, the actual graph, and how it behaves together correspondingly with the derivative, okay? And so what about, so in this particular graph right here that I'm looking at, what if I move that point to exactly hit x equals 2, and of course I'm going to have a very challenging time getting that precisely on scene right there, but so it looks like we're going to have about, all right, so right there, okay, I'm trying to, right, so that right there, then I notice I have a horizontal tangent line, so I can tell that graphically speaking, I can see that our function f prime of x, the slope of the tangent line has to be equal 0. So right at that point, when x equals -2, then I'm sure that I still don't know what my f prime of x looks like, because I never knew what my f of x looked like. I mean, I only knew the graph, but I didn't know the actual function. So I would fail to know the general derivative. But I know for sure the derivative must equal 0 for x equals -2. Okay? And so in that way, back to the graph itself, if I now observe when I bring my dragging points in anywhere inside of that zone between x equals -2 and x equals 2, as I said, between x equals -2 and x equals +2, then see, now that's why I'm putting my point anywhere between -2 and 2. So in that entire region right there, in that entire interval, in that entire zone right there, then it looks like no matter where I put my tangent point in that region, my green tangent point is pointing down right here. And so in that way, another conclusion I can be made, even though I never knew what exactly my slope of my derivative of the function is, but I can tell that my f prime of x as a function must be a negative function. Okay. So f prime of x must be a negative value for in this interval, for x being anywhere greater than -2 but less than 2. That's how I can make those conclusions right there. And so furthermore, and again observing my graph here, and if I'm now trying to hit that point x equals +2, and of course I know for sure I'm going to have a challenging time to hit that, but I'm about right there. So when x equals 2, then my tangent line becomes exactly horizontal, or slope equals 0. So back to my explanation again. So now I'm looking at so what we're having here is we're going to have f prime of x must equal 0 for when x equals precisely +2. And so now further on, you can now tell in that way where I'm going, then needless to go too far. But then when I move my point to anywhere greater than 2 right here, for x anywhere greater than 2, then I am going to have positive slope for my tangent line. And so in that way, right, my derivative must be positive. The derivative as a function must be positive value for x value being in that entire interval greater than 2. Okay, and so putting all that pieces together, let's roll back to the f of x equals x squared function again. All right, and give me a moment to erase the board. And so after we have taken notes on all that, and if we're going back to the function f of x equals x squared, okay, and let's pretend that we didn't know we didn't even find its derivative, but now we found earlier, and maybe let me quickly put up the graph as well. Give me 1 second. All right, so here we are on it again. Now I can put it on screen right here. And now as I show the actual tangent, okay, then we can draw, let's pretend that we never found the actual derivative. Don't worry about the 2x that we found. Let's just say we know that this is the graph of some function. And so in this zone, when x is equals to, in this zone to the left-hand side of x equals 0, then we saw that we know that our f prime, without knowing what that is, it has to be less than 0 for x is being less than 0. And the same function here, but we know its derivative. I'm talking about if we never found that f prime, but we would know that f prime has to be equal to 0 when x is precisely equal to 0. Because on the picture, it's right here on the picture, if I drag my point right to be right at x equals 0, and of course, like I said again, I'm going to have such a challenging time. Okay, let me zoom it in a little bit. Hopefully it helps. But if I drag my point to exactly at x equals 0, then I would have a horizontal tangent, and that would mean my f prime of x has to particularly equal to 0. I'm talking about if we regard to this as a function, then the function output value for f prime has to equal 0. And so say the same way, if that f prime of x has to have outputs greater than 0, because now we already agree that f prime is a function. So function has output value. And so I'm talking about the output value behavior. So f prime has to have output value greater than 0 for x being greater than 0. Simply because the graph is indicating when I'm dragging this point to the right-hand side. Okay, and my slope of the tangent line anywhere here is a positive slope. The line is rising, and so f prime of x has to be positive for any x value greater than 0. So in that way, there is this kind of problem that can become quite convenient right here for a lot of us. Okay, so let me quickly prepare my graphing screen right here, and I'm going to put the graph back on for everybody. Right, so all right, so here we are. So now I'm ready to put it on. There we go. So what we have here is a picture that has two graphs together, and I can tell anyone, and let's call this problem, you can go ahead and pause the video, and maybe I can even put that on one whole screen so everybody can take notes carefully. And so take photo shots of your graphs and the two graphs together, so one picture with two graphs, and take a photo shot or take a copy of that or whatever, and then we are going to call that, this is going to be our example 5 in this lecture. All right. So in example 5, the introduction here is what we have here is we're gonna have given the graphs of our function f of x and also of our function f prime. So at this point of our learning, f of x is a function, as we already knew, and f prime is also a function of x. We don't know any of them. We don't know what function, we only know the graphs, we only see the graph, and we only see f prime. But so now the challenge here, if we're looking back on the picture, the challenge here is that in this problem here, no one is telling you which one between the blue and the red, which one is the graph for f and which one is the graph for, so can this be the graph for f or can this be the graph for f prime? If so, which one here is the graph for f prime and which one here among the two is the graph for f? And so back to our ultimate goal of the example, we want to identify the graph of f of x and the graph of f prime of x. That's the challenge we are being given for this kind of example right here. Because like I said, we only saw the two graphs. One of them is in red and one of them is in blue, and the problem is telling us that those two graphs, they are, one of them is the graph of the original function f of x, and the other one is the graph of f prime. But which one is which? Which one is at the blue or the red is for the original function, and which one is for the derivative? Okay, and so in that way, we are going to work it out together right here. All right, so now I'm going to bring the graph a little bit part of my screen right here for that. And of course, I'm not going to use this dragging point anymore. So let me hide that away, and we don't really need that. Okay, and so I purposely put these 2 points here, but I hope without those points you can also tell, because we still have grids here in the end. Okay, but now the way how I observe, and of course for me being in the role of the teacher here, I have done these for years, so maybe I can explain this maybe I can see this more quickly than anybody, but you can always pause the video and make your own estimates before I throw my reasoning in. But so if we're looking at this one right here and observe my graph, and maybe let me put it on full screen here to make that more obvious, a lot more obvious right there. Okay, so if we're looking at this graph, there's the reason why these 2 points are being given here. It's all in the purpose of assisting our view of the graph and to make it more clear right here. But so right at x equals -2 and right at x equals 2, for example, let's say, think about the red graph. If the red graph right here, if x equals -2, then on the red graph we have, if we place a tangent line here, we're going to have a horizontal tangent line. If we place a tangent line on the blue graph at x equals -2, we're going to have some tangent line, and we don't know what that slope is. Okay, but for sure, think about it. I can use my mouse cursor right here and trace, and you can see that, we can see that if we put a point right here as a tangent point and place a tangent line through, we're going to have a 0 tangent line. So 0 tangent line there at x equals -2 means our, okay, so just that, let me make some conclusion. We have had, and I have to, so the way how I reason that, and here it's just because the first time anyone being exposed to this kind of problem, so I have to write it down, but when you're fluent with this kind of problem, you can go a lot faster than that. And there's not even any written steps that needed for this. But see, when x equals -2, as I pointed out, then it looks like the red curve, okay, the red function, the red curve, it has, if we place a tangent line there, it's going to have mt equals 0. For the blue one, it's going to have, the blue curve is going to have some mt value, but all I see is it was some, it looks like it was some negative slope for that. But then, okay, but then that's, if I get back to the graph right here, okay, so notice how the blue is actually crossing through the x-axis right at x equals 2. I mean x equals -2. Okay, so does that add some further understanding? So I'm going to put back this thing right here. So we know that blue has some slope. If we place a tangent line on the blue one right here, then we know we're going to have some negative slope. The line was pointing down, and it's still on your picture. But this information doesn't look like it's helpful. But the further one we know is the blue, okay, invertible. So these are two properties we notice at x equals -2 right here. The blue hits the x-axis. Am I correct? Okay, the blue cross through hits the x-axis. Okay, so hits the x-axis means what? This right here ultimately means, graphically speaking, okay, the whatever function for blue, the function for blue has to equal 0. Okay, and then let's check again. I'm going to tackle down at the other point. How about at x equals 2 right here? At x equals 2. Okay, I'm going to leave this board actually. As x equals 2, what's the behavior of red? Red seems like if we place a tangent point here and put a tangent line here, we have again a tangent point, I mean a tangent line being horizontal tangent line. And so that means for red, the tangent line is going to have a slope equals 0 again. And For the blue, if we place a tangent line right at x equals 0 right here, we're going to have some tangent line being positive, but it doesn't look like it's relevant to any of the work we're doing. But the blue line is crossing through the x-axis at x equals 0. So for the blue, this is what caught my attention. For blue, it looks like it hits the x-axis again. Okay? So blue is some function, and either one of these two, blue and red, one of them has to be the actual f. And so observing the behavior like this, then I'm starting to suspect, how's that? I'm starting to suspect that f of x is the red one. Okay? And if f of x is the red one, the other one is, of course, have to be the blue. But now we're not going to just, because we only rely on little information so far. So f of x is red, and f prime is blue. It's the blue graph. But now we're not going to just simply stop right there. Let's confirm a little more. Let's confirm a little more. And so in this way, let's see how it happens right here. So now between inside of that interval, for the red itself, from what we've learned, if this red here is the actual function, then it looks like placing a tangent line anywhere inside of this interval between -2 and 2, then we're going to have a negative slope. A negative slope means, again, f prime has to be negative. So look at the blue. The blue is below the x-axis. The blue is below the x-axis, meaning, okay? So let me write it this way. So inside of that interval, so we kind of, this is just only kind of like our guess so far, and we want to confirm it. So we confirm by looking at that interval between -2 and 2. Okay? It looks like red now kind of believed to be the f of x has a negative slope. And negative slope is consistent with the fact that f prime has to be negative. And if f prime is negative, does that look consistent with the blue? Okay? It looks like blue is below the x-axis. Okay? Aren't these two pieces of information consistent with each other? Okay? So now we are further confirmed that f of x is the function and f prime is blue. But let's check even further and nail down all the other information. So now when x is less than -2, the red, if we place a tangent on the red, then it's looking like we have a positive tangent line. Okay, so now really let me put a tangent up. Okay, if we put a tangent line here for, all right, so if we place a tangent line anywhere for x less than -2, then the tangent line is pointing up. The tangent in green is positive slope. That's consistent with blue being above the x-axis. Positive value for f prime right here. Okay, so f prime now is more firm to be the blue one. And then same way, if now we place a tangent line anywhere to the right-hand side of x equals 2, then tangent line is pointing up again. Consistent with f prime is positive. See, f prime is above, the blue curve is above the x-axis. And that is how now we are completely firm that among the two graphs given, one of them is blue, the other one is red, but now the red one is the graph for f of x, and the blue one is f prime of x. And that's the kind of problem that we are doing for this. All right.